All right, guys, so you don't need to write this down because you've already got the notes in front of you and it's already labeled. But guys, let me just give you the big idea for the day. So here's where we're at. Over the last 2 class periods, which you guys understand never happens in this class, guys, we just spent 2 class periods learning to draw Lewis dot structures. These are important. You're going to find out that the next 2 units after Christmas all depend upon your ability to draw Lewis dot structures. What we're going to do today to wrap this up is we are going to take these flat, lifeless, inaccurate Lewis dot structures and we're going to figure out what these things look like 3-dimensionally. Now guys, to understand that, there are some terms and concepts that you need to get, and so the beginning of this is going to be 3 terms that you need to understand. It's all in your notes. You're going to find out those ideas are bonding domains, Vesper Theory, and then 1 additional thought. And then guys, when we're done with that, you're going to take this notes page and just do it with me. You're going to flip this thing over on the back. And I'm going to give you the double top secret decoder key that will allow you to take these Lewis dot structures and figure out what these things look like 3-dimensionally. And we're going to play with models, and we're going to play with bubbles, and we're going to do all of this stuff to get a sense of what these look like 3-dimensionally. And then guys, on Monday, we're going to put model kits in your hands, and you guys are going to start playing with these, and you're really going to understand what they look like 3-dimensionally, and then we'll do the test on Wednesday. You guys ready to go? That's the overview of the day. Okay, so guys, do not write this down because it's not in your notes page. This is all conversational. It's basically what we just said. So guys, now you are good at drawing Lewis dot structures. And Lewis dot structures are really good at a few things. They tell us the order that the atoms bond. They tell us the types of bonds that form single, double, triple bonds or unbonded lone pairs. But guys, they don't tell us a thing about 3-dimensional structures. There are no 90-degree angles in any of these molecules. So, what do we need to do to look into the 3rd dimension? Well guys, that's what we're going to do today. We're going to figure these things out 3-dimensionally. So, to do that, there are 3 things we need to talk about, and here they come one at a time. The first one are what are called electron domains. Write this down with me because it's in your notes. See it? Yep, it's on the front. Flip it back over. So guys, what are electron domains? Well, let's do this. So you're watching Nova, right? And it's okay to admit publicly you watch Nova. I do too. So guys, you're watching a Nova special on Channel 7, and they're out in the middle of the Serengeti, and they're talking in really hushed voices, and they're saying, now we are in the domain of the hippopotamus, or whatever. And so guys, when they're talking about entering into the domain of the hippopotamus, what does that mean? Where are you? What does that mean to be a domain? It's the place you find hippopotamuses, right? So if you enter into the domain of something, you're entering into the place where those things hang out. And guys, it doesn't matter if there's 1 hippopotamus or 1,000 hippopotamuses, it is still the domain of a hippopotamus. That's a fun word to say, hippopotamus. So guys, if you're in the domain of an electron, where are you? In the place where electrons hang out. So guys, electron domains are the spaces that electrons occupy around the nucleus of an atom. But guys, we already have a name for those things, don't we? We call them orbitals. Remember that? Those imaginary clouds where electrons appear to occupy? So guys, when we talk about electron domains, what we're actually talking about is orbitals. But the thing that you learn from drawing Lewis dot structures is that these orbitals, these domains, can either be involved in bonding domains, or they can be non-bonding domains, so they can be each. So how does that fit into your notes? Oh gosh, I already wrote it down for you. Look at me. Okay, so guys, let's talk about bonding domains first. Bonding domains are shared pairs. But guys, you see how that says bonding domains and then the little tick mark that's underneath it? That's not, did you guys all write that down right there on that tick mark? Sorry, you're okay. You shouldn't have. You should have just gone bonding domains and then kept going are shared pairs. But you're okay. But guys, here's the thing you need to understand about bonding domains. Any type of bond counts as one domain. So you can just write that down there too and you're fine. But now, guys, I've really screwed you up because now non-bonding domains are the lone pairs, but you can actually write that down where the tick mark is because there's nothing else to write down. So, guys, this is it. Electron domains are the places that electrons seem to occupy. Those can be bonding domains or they can be non-bonding domains. Guys, the bonding domains are the shared pairs and the non-bonding domains are the lone pairs. So guys, here's the trick. See if you can make this connection. So on the last two homework assignments, we've been counting the shared and lone pairs, right? Guess what you were actually counting? Domains. So guys, when you were counting shared and lone pairs, what you were actually doing was counting the domains. So now we're going to call them domains rather than calling them shared and lone pairs. But guys, what you need to do then down here in that space that I gave you is draw the 4 types of electron domains. You'll notice I gave you space to do that and I even labeled it for you. So guys, lone pairs, 1 domain. A single bond, 1 domain. A double bond, 1 domain. And a triple bond is 1 domain. Again, guys, it doesn't matter how many electrons are in the domain. It could be 2, it could be 4, it could be 6. It's still 1 domain. So guys, that's big idea number 1. There are these things called electron domains. They're simply the places where electrons hang out. A lone pair is a domain, a single bond is a domain, a double bond is a domain, triple bond is a domain. Questions? That's big idea number 1. You okay? Okay, so do this. Don't write this down. Guys, here's the one you got to memorize, right? Don't write it down. But here's what you've now got to be able to do. And guys, please don't blurt out the answer. Let people think. So guys, looking at this carbon right there, and again, please don't say anything yet. How many domains are on that carbon? Count them. Now let's talk about it. How many domains? There's 4. So guys, the idea here is each of these single bonds counts as 1 domain, so there are 4 domains on that carbon. Does that make sense? Okay, so what about this? How many, and again, give it a second, but how many domains are on that carbon? There's 3. So the idea, guys, is this is 1 domain, this is a domain, and then that double bond is 1 domain. Yeah, there are 4 electrons in there, but it's 1 domain because all 4 of those electrons are in the same place. Get the idea? Okay, so what then about this oxygen? And let's just say it. How many domains are on that oxygen? 4. So guys, 2 of these are single bonds. Those are bonding domains. And then 2 of these are non-bonding domains. So we've got 4 domains, 2 bonding and 2 non-bonding. You good on that? Okay, so what then about that oxygen? How many domains? 3. Guys, if you understand this, you know that that's 3 because this double bond is 1 domain, that's a domain, and that's a domain. Questions on, and guys, that's what you've got to be able to do to think 3-dimensionally is count domains. This is important. So what questions do you have? You guys okay? Okay, so that was big idea number 1. Can we go on to big idea number 2? Okay, so guys, big idea number 2 is what is called Vesper Theory. And you'll notice this is in your notes. So guys, this is now the question we're going to answer. What do these domains do to each other? When these domains surround the same atom, what do they do to each other? And the answer is they Vesper. So what does it stand for? This stands for, and you can write it down, the valence shell electron pair repulsion theory. Yes. I know I screwed you up with the tick marks, huh? Now you don't trust me. I'm back on track, y'all. So guys, the valence shell electron pair repulsion theory. So guys, what on earth does that mean? Well guys, what are valence shell electron pairs? Domains. That's just a fancy term, guys, for domains. Valence shell electron pairs are the domains, and what does it mean that they repulsion? They get away from each other. And guys, why would pairs of electrons get away from each other? They're all negative, and they don't attract, they repel. This is kind of one of those really fancy ways of saying something really simple, which is just electrons want to get away from each other because they're all negative and they repel. So guys, fundamentally, it just says this: electron domains repel each other. And when they repel, this causes them to get as far away from each other as they possibly can. Okay, guys. Oh, go ahead, Cam. Good. Yes. Yes. Yeah. They don't orbit each other, but they do influence each other. We can actually, it's crazy science now, they can actually measure that influence. That as electrons from separate orbitals or domains start to come together, they do interfere and they actually affect each other's orientation. It happens with electrons as well. It's what is called angular momentum, because whether it's the Earth or whether it's an electron, it's spinning. And I don't know if you've ever done this. Have you ever taken, like, I've seen it done with a bicycle wheel, where you grab a bicycle wheel by the axle and you spin it, and it doesn't want to turn like it wants to. Like, it's how a gyroscope or a top works. That something that's spinning wants to always point in the same direction. Electrons are the same way. They don't want to tilt, just like the Earth doesn't want to tilt. But if you take one of those electrons and make it tilt, the electrons around it will as well. Yeah, and so they're measuring what's called angular momentum. It's pretty crazy stuff. Okay, you guys good here? We okay? All right, so guys, big idea number one. These things that we used to call shared and lone pairs are actually called electron domains, and you guys just demonstrated that you know how to count them, because the little bit that's different is it doesn't matter if it's a lone pair, a single bond, a double bond, or a triple bond, it's one domain. You said you were good on that. Thought number two, and it's really simple, don't overthink this, is those domains push on each other and they get away from each other. You good for number two? Because here comes number three, and then we're going to get into the back of the page. You ready for number three? Guys, number three goes like this. Not all of these domains have the same shape and size. So guys, what you're going to find out, and you don't need to write this down because it's sort of the introductory idea, these things don't have the same size. So now picking up where it says bonded electron domains. Guys, bonded electron domains, just write it down with me, bonded electron domains are long and skinny. So the question is, why would bonded electron domains be long and skinny? And the answer is because they're being pulled on by two nuclei. And I'll show you what I mean in just a second. So guys, check it out. This is the idea. Remember, these electron domains are like clouds, right? So allow this rubber band to be the shape of the cloud. Well, if this is a bonding electron domain, then that's holding two nuclei together. So imagine my fingers are the nuclei, the protons, they're positive. So if this rubber band is the cloud of electrons, this rubber band is being pulled on by two nuclei, and when you pull on something in two directions, that something, the cloud, the domain, becomes long and skinny. So we're going to draw it like this, and you're not going to have space to draw it below, but you could draw this over here to the right if you want. Guys, this is actually what a bonded electron domain looks like. The red dots, well, it's even labeled, the red dots are the nuclei, the blue is the electron cloud, that's the domain, and that domain is being stretched in both directions because it's being pulled on by two nuclei. And guys, I know that this is just writing stuff down. We're almost done with that, and we're going to start thinking here in a minute. Some of you right now are going, no, I was actually much happier just writing stuff down. I know. But we're going to try thinking too. So guys, that is what a bonded electron domain looks like. So now let's talk about non-bonded electron domains. Guys, as the name suggests, a non-bonded electron domain, a lone pair, is not involved in bonding. As a result, it's short and fat because it's only being pulled on by one nucleus. So guys, let me show you what I'm talking about with the rubber band as soon as you're ready, and then I'll let you draw the picture, and then we're going to flip the paper over. Okay, so guys, the idea then is this. Bonded domain, long and thin, right? Being pulled on in two directions. Well, guys, if we've got a non-bonded domain, look at what happens to the shape of that rubber band. The idea is that with a non-bonded domain, it's not being pulled in two directions. It's only being pulled on by the one nucleus, and as a result, it becomes like short and fat because it's only being pulled on by one nucleus instead of two. So guys, the way that we draw that is more like this. A non-bonded domain, a non-bonded pair, is actually shorter and fatter because it's only being pulled on by one nucleus. So guys, there you have it. Those are the three things that you need to understand in order to move forward. First idea is we are not going to call them shared and lone pairs anymore. We're now going to call them domains. And domains are the places we find electrons, a single bond, a double bond, a triple bond, or a lone pair. Those are all one domain each. Then, guys, we found out that these domains push on each other and spread out. We call that Vesper Theory. And then, guys, the last thing that we learned is that these domains don't have the same shapes. Bonded domains are long and thin. Unbonded domains are short and fat. Yeah. Well, sort of, but what we're really talking about there, Cam, if I could, is like one of the lobes of a p orbital. That's actually what it is. What you're looking at here is one of the lobes of a p orbital, and in this case, that lobe is short and fat because it's being pulled on by one nucleus, and here that lobe of the p orbital is being stretched because it's being pulled in two directions. Is that, yeah, I didn't plan on getting into that, but that's actually really what we're looking at is the lobes of p orbitals. So, you guys good? You ready to flip this thing over? All right, here we go. Once again, guys, making sure domains push on each other. Bonding domains are long and thin. Non-bonded domains short and fat. You good? Okay. So, guys, flip this thing over. Let's look, literally, let's look at the organization of the back of this table. The back of the paper. So, guys, notice the way that this goes. So you hold it at arm's length, and you'll notice that, first of all the information that you're going to write down is organized into tables. Now, guys, what do you notice about the size of those tables as you go down? The tables get smaller. It goes, well, first of all, this. What do you notice about the columns? They're all the same, right? It goes molecule, Lewis dot structure, bonding domain, non-bonding domain, angle. It's all the same. So we're going to talk about the same information in all three of these tables, but then you'll notice it goes from four rows, what are those called? Rows. Okay, so 4 rows to 2 rows to 1 row. So guys, you're going to see there's a narrowing of information. But then, guys, notice what's written in bold. How are these things separated? By the number of domains. So guys, allow yourself to remember, what are domains? Single bond, double bond, triple bond, lone pair, right? So what we're going to do is we're going to organize in our brains, we're going to organize this information based on the number of domains. So first we're going to talk about 4 electron domain molecules, then we're going to talk about 3 electron domain molecules, then we're going to talk about 2 electron domain molecules. You get the idea? You see the organizational pattern? You're good? Okay. So guys, join me at the board. Don't write any of this down. Let's talk. So guys, we are now going to talk about 4 electron domains. Okay? Now remember what we know about these domains. Vesper theory says they push on each other, right? And when they push on each other, they want to get as far away from each other as they possibly can. So guys, as a result, I have a question for you. Don't write it down, but think about this. The question is this. When 4 objects, those are going to be our domains, when 4 objects surround a central point, that's going to be the atom in the middle, when 4 objects surround a central point in 3-dimensional space, what angles are created if these objects are as far apart as possible? So guys, let's make the connection. What we're talking about is domains. And now we're going to talk 3 dimensions, but guys, why would those domains be as far apart as possible? That's Vesper theory, right? Okay, so let's talk about it generically, and then we're going to talk about it relative to atoms. So don't draw this, but guys, this is the question that I'm asking. Here is our central point. Now, if I put 1 point around that, that's the blue dot, and eventually we're going to do 4. So guys, here is 1 object around a central point. Now, if I want to put a second object as far away from this as I can, where am I going to put it? Directly across, right? Right there. Now, what if I want to add 2 more points for a total of 4, 2 more points as far away from those as I can? Where am I going to put them? Top and bottom. You get the idea? So what I have now drawn is 4 objects surrounding a central point as far apart from each other as I can. Now watch this. Let's connect these with lines. And guys, when we do that, what angle is formed right there? 90-degree angles. So guys, do we now know the answer to the question? Because it says this. When 4 objects surround a central point in 3-dimensional space, spreading out as far as they can, what are the angles? And it looks like it's 90 degrees. Is that the answer to the question? Why not? What's missing? 3-dimensional. Guys, this is 2-dimensional. If this was 2-dimensional space, then the answer would be 90 degrees. But the answer is not 90 degrees because we are now going to talk 3-dimensional. So guys, check this out. This is cool. What does this have to do with the question that's on the board? Do you see the connection? Say it again. Yeah. Guys, 1, let me hold on to that. 1, 2, 3, 4. Get it? So we've got 4 points, and let me tighten this up a little bit so this works better. So guys, we've got 4 points represented by the 4 corners of this pyramid. So if that's true, where is the central point? Hanging in the middle. There's nothing there, but the central point would be at the tip of my finger. Get the idea? Okay, now what about this? So we understand that these are 4 points in 3-dimensional space. Now, here's the next interesting question. What did I do when I made this to guarantee that these 4 points are as far apart from each other as possible? When I built this, I did something smart that guaranteed that those 4 points are going to be spread out as much as they can. What did I do? I'm not going to tell you. What did I do to make sure those are as far apart as possible? Come on. This is the awkward moment in the screencast. What did I do to make sure they're spread out as far as possible? Didn't use a it was actually even easier than that. Go ahead. Made the straws the same length. Right? Guys, if I cut all of these straws the same length, I am then guaranteeing that all the points are as far apart as possible. So, this red piece of plastic does in fact represent the question on the board. You get it? Now guys, watch this. I am going to show you that the angles that are created are not 90-degree angles. And I'm going to do that by coating this thing in just simple bubble juice. I bought it at Walmart. But guys, what I'm going to do is I'm going to coat this in bubble juice. And guys, what do we know about bubbles? We know that bubbles are very, very weak. And because bubbles are very, very weak, these bubbles are going to connect these 4 points as easily as they possibly can. And when they do, got to get this mixed up a little bit. When they, I pop my P's, and that pops the bubbles. There we go. So guys, what I'm now doing is connecting these 4 points in 3-dimensional space. And depending on the angle that you're looking at this from, you can see, can you see that? The central point right there? And guys, you can see that that angle, this is doing a lot better than it normally does. Guys, you can see that that angle is not a 90-degree angle. Is it greater or less than 90 degrees? It's greater than 90 degrees. 90 degrees would be right there. That angle is greater than 90 degrees. Does anybody happen to know what it is? Then I'm just going to tell you. Guys, that angle is actually 109.5 degrees, and there's a place for you to put that in your notes. So guys, these angles are not 90 degrees. They would be in 2-dimensional space, but in 3-dimensional space, they are actually 109.5 degree angles. So now, rather than look at this in terms of bubble juice, guys, and by the way, I should say that I'm dripping bubble stuff everywhere. Be careful when you leave class today because it makes the floor slick. But guys, now let's take this out of this, and now let's talk about this. Do you see the connection? Guys, this shape is the same. Do you see it? But this is what it looks like as a molecule. So when we have those 4 domains around a central atom, these are 109.5 degree angles. So we're lifting this out of the realm of bubbles and now talking about it in the realm of molecules. And guys, this is this. So this thing is what we, well, I'm not going to tell you the name. We know that these are 109.5 degree angles. What we need to do is name it. So guys, what is the geometric term for 4? It's quad, or somebody even said the whole thing. It's tetrahedral. Guys, these 4 points in 3-dimensional space make a shape which we call a tetrahedron. So the name of this is tetrahedral. So now guys, look at what we're going to do with this. We are now going to look at all of the molecules that have tetrahedral domain geometries. And what does that mean, tetrahedral? It just means 4. So looking now at your table, we are now going to look at all of the 4 electron domain molecules. We call these tetrahedral domain geometries. Tetra means 4. So guys, write these down with me. CH4, NH3, H2O, and HF. Guys, all 4 of these are examples of molecules with tetrahedral domain geometries. So guys, the next thing we're going to do is we're going to draw their Lewis dot structures, but I'm just going to give them to you because you've already drawn them. And guys, I would strongly encourage you to draw these like I did. You know that left, right, up, and down doesn't matter, but this will be easier if you draw them like I do. And guys, I'm just giving these to you because you've already drawn these in homework. These were actually in all of your homework assignments over the last couple days. So I know you've done them, so I feel comfortable just giving them to you. You guys okay? Y'all caught up? So guys, it's critical that you can answer this question. 4 domains. Guys, watch. You got to get this. On the carbon, oh gosh, I can't touch the board. Hold on. Bump, 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 bump. Good. Okay. So guys, on the carbon, do you see the 4 domains? They're all bonding domains, right? Now guys, look at the nitrogen. Do you see the 4 domains? But what's different? Now one of them is a non-bonding domain. On the oxygen, do you see the 4 domains? But now how many are non-bonding? 2. On the fluorine, do you see the 4 domains? But now how many are bonding? Are non-bonding? 3. So guys, what I've done is I've given you 4 molecules, each with 4 domains. On the first one, there's no non-bonding, then 1 non-bonding, 2 non-bonding, 3 non-bonding. See how we're organizing this? Now let's pull this together. So guys, what we're going to do now is we're going to work to the right. So guys, looking, and we're just going to go across. Do this with me. Looking at CH4, how many of those domains are bonding? Write it down. How many of those are non-bonding? 0. Good, good, good. You're doing it. So all 4 are bonding. None of them are non-bonding. And guys, this is what it looks like. See it? This is what this molecule looks like. So guys, what are those angles? You already know the answer. 109.5 degree angles. And what do we call this shape? Tetrahedral. So guys, this is a tetrahedral molecular geometry as well. So now you're going, wait, I thought all of these were tetrahedral. Guys, they're all tetrahedral domain geometries. This is also a tetrahedral molecular geometry. Let me explain that by looking at the next example. Guys, NH3. Looking at NH3, how many of those 4 domains are bonding? 3. How many are non-bonding? 1. Guys, the model looks like this. See it? This is what the model of this molecule looks like. But guys, what is not represented in this model? The non-bonded pair. So guys, let's remind ourselves. So what we've got here is we've got our 3 bonding domains. The thing that is not represented, and guys watch really close, the thing that is not represented is the non-bonded pair of electrons. Where is that in this molecule? It's on the top. It's right here. Guys, there's an unbonded pair of electrons sitting up here that you can't see because it's just a cloud of electrons. But guys, remind yourselves, what did you learn? Oh, I almost kept it. Guys, what do these bonded domains look like? Long and thin. What do the non-bonded domains look like? Short and fat. Now guys, watch my fingers really closely. You ready? Watch. So what's missing from this picture? The unbonded pair up here. And this unbonded pair is short and fat, and it pushes these down. Did you see me do that? So guys, the idea is that this unbonded pair up here on top pushes the bonded electrons down because this is short and fat, and it pushes these down. So guys, what happens to that angle right there if this big old fat thing pushes? It gets smaller. So guys, the angle in this molecule is actually less than 109.5 degrees. If you're curious to know, it's actually 107 degrees. You don't need to know that. But you just need to know less than 109.5. Now guys, here's the trick. Now we got to name this thing. And this thing is not tetrahedral, is it? So how could we describe the shape that is in my hand? You ready? This is pretty good. Do you see that it looks like a pyramid? Do you buy that? It looks like a pyramid. And guys, how many feet does the pyramid have? 3. So what's the word for 3? Tri. So guys, this is what is called trigonal pyramid. So what's the connection? Well guys, this molecule has 4 domains. So its domain geometry is tetrahedral, but only 3 of those are bonding domains, so its molecular geometry is trigonal pyramid. You get the idea? Let's do water. So guys, the next one we're going to do is a water molecule, H2O. How many of those 4 domains are bonding? 2. How many of them are non-bonding? 2. So guys, water looks like this. Check it out. So guys, what is missing from this model? 2 big, fat, unshared pairs of electrons, right? And what are 2 big, fat, unshared pair of electrons going to do? Bend this down even more. You don't need to know the number, but it actually goes down to 104.5 degrees. Don't worry about that. You just need to know that it's, again, less than 109.5. So now, guys, we got to name this. This is not tetrahedral as a molecule, and it's also not trigonal pyramid. How are we going to describe what this looks like? This is actually really a letdown. Guys, this molecule we actually just call bent. No, bummer, right? Tetrahedral, trigonal pyramid, bent. But that's it. Okay, so now, guys, we've got to do HF. Looking at the fluorine, how many of those 4 domains are bonding? 1. How many are non-bonding? 3. Oh, gosh, don't look. You looked, didn't you? Darn you guys. All right, so guys, let's talk as if you didn't. So guys, this is the molecule, right? Really simple, just HF. Again, what is missing from the picture? 3 big unbonded pairs of electrons. But guys, what's the angle? There isn't one. Because guys, make sure you're clear on this. You know this from math. 2 points do not define an angle. What do they define? A line. Guys, there is no angle in a line. So 2 points define a line, so the angle is undefined. That's not the same as 0. There is no angle because there's only 2 points. And the name that we give that is straight. You can't, and you'll see why in just a second. Linear is a completely different structure. Yeah?
So is the angle measurement between each of the atoms or each of the bonds?
So those are the same because the atoms line up with the domains. So the angle that we're measuring is the hydrogen-nitrogen-hydrogen angle, or the hydrogen-carbon-hydrogen angle, or the hydrogen-oxygen. So it's that angle. Okay, so guys, in summary, and I don't remember if I gave you space to write this. I did not. But guys, in summary, check this out. What do all 4 of these molecules have in common? Or, yeah, let me zoom out. So guys, what do all 4 of these molecules have in common? And don't write this down, they all have tetrahedral domain geometries. All 4 of these have 4 domains, so they all have tetrahedral domain geometries. And then notice, oh gosh, my clicker is really killing me. Then guys, notice that their molecular geometries are depending on how many of those domains are bonding domains and non-bonding domains. No, you don't need to. You okay? Okay, let's do 3 domains. Ready? Same question. When we separate 3 objects around a central point in 3-dimensional space, what are the angles that are created? So guys, here's our circle. There's our 3 points. You get the idea? So we've got our circle. Now we've got 3 points in 3-dimensional space. So now instead of 4, we're looking at 3. We've got 1, we got 2, we got 3. They're spread out as much as they possibly can. Guys, what is the angle between each of those lines? Right, because it's 360 divided by 3, right? So it's 120 degrees. But guys, again, this is just 2-dimensional. So what if we spread this out into 3-dimensional space? What do the angles become if they're spread out as much as possible? The same. The answer is not different in 3-dimensional space. So guys, in 3-dimensional space, the angles that are created are 120-degree angles. Guys, let me show you what I'm talking about. It's this guy. That's this molecule. You've drawn this. This was number 1 in the homework. We'll talk about it more. Well, remember, Cam, you asked about it. So guys, this is what we're talking about. So look, what are all these angles? 120, 120, 120. Good? Now, guys, we've got to name this. So how many points does it have? 3. But guys, notice this. Watch my hands. This is no longer a pyramid, right? This is flat. And if something is flat, it is in the same plane. Do you guys know about planes? So guys, this is flat or in the same plane, so we call this trigonal planar. Okay, so let's go down to our table. So here's our table, here's our examples, here's our Lewis dot structures. So guys, the two examples that we're going to look at are CH2O and NO2 minus. And guys, you'll notice that I didn't put NO2 minus in brackets and add the negative charge. It should be there, but it just got distracting, so I didn't put it. Actually, I did put it, and then I deleted it because it was in the way. Do you guys like the bubble thing? That's not bad, huh? I wish I could say I came up with that on my own, but actually another chemistry teacher showed me that one. You want to have a really funky experience? Go to a meeting where they get a bunch of chemistry teachers in the same room. They're a weird bunch. You'll notice I said they and not we. I don't count myself amongst them. You guys all caught up? They tend to take themselves way too seriously. You guys good? So, hey, let's make sure that you're really clear on this. Guys, what do these two molecules have in common? 3 domains. Not bonding domains, but 3 domains. Guys, here we've got 1 domain, 2 domains. Is that 3 domains? Or is that 4 domains? Just 3, because a double bond is 1 domain. So 1, 2, 3 domains. Do you see it? Okay, now go down here to the nitrogen. Hey, this one's got it all. How many domains? 1 domain, 2 domains, 3 domains. So guys, both of these molecules have 3 domains, so they have tetrahedral domain geometries. Now we're going to figure out their molecular geometries. So guys, let's do this. Looking at the carbon, how many of those 3 domains are bonding? All 3. How many of them are non-bonding? 0. So now guys, and I've already showed this to you, it looks like this. This is flat. It's got 3 points. It's got 120-degree angles. So this has got 120-degree angles, and it is trigonal planar. I need to put new batteries in my clicker. This thing's being horrible. All right, so now guys, looking down at the nitrogen in the middle of NO2. So again, we've got 3 domains, right? But how many of those are bonding? Just 2. We got a double bond and we got a single bond. So 2 of those domains are bonding, and then 1 of them is non-bonding. And guys, this is what this looks like. So we've got the double bond, we've got the single bond. Again, guys, what's missing from this model? The unbonded pair of electrons. And where is it? Up on top, we've got this big, fat, unbonded pair of electrons. And what does that do to these guys? Pushes them away. And what happens to that angle? It gets smaller. Smaller than what? 120. So guys, this angle will be smaller than 120. Not smaller than 109.5 because it didn't start there. It's smaller than 120. And somebody already said it. What are we going to call this? Bent again. I know. But now guys, check this out. Please hear this carefully because this might trip you up. Guys, why is there not a third set of boxes here where we go 1 bonding and 2 non-bonding pairs? Why did I not give you 1 bonding and 2 non-bonding? Because you already know the answer. Because guys, if there's only 1 bond, then there's only 2 points. And if there's only 2 points, what's that going to be? Undefined and straight. So guys, I didn't give you the example of 1 bonding and 2 non-bonding because it's the same for all of the different structures, because that would be straight and undefined. So anytime you've got 1 bond, it's always straight and undefined. So again, guys, this then is the idea. Oops. Oh, did it go away? I wonder if it went away. Just a second. Oh, my notes are over here. Sorry, guys, just a moment. There was one other thing. Maybe I used to have a thing in my notes where I described what, oh, I just took it away. Yeah, I used to have a thing that described. So are you okay with that idea that we didn't do 1 and 2 because it would just be undefined and straight? Okay, so guys, last one and we're done. Goes like this, and then this is crazy. We've only got 20 minutes left, right? You're still going to get your homework done today. Guys, check this out. So guys, last question. Now we're looking at 2 domains. So when 2 domains surround a central atom in 3-dimensional space, what do we do to get them as far apart? So guys, here's our point, here's our circle. We're going to put 1 object there. Where does the second object go? Opposite it. And guys, what is that angle? 180 degrees. But guys, we're not going to call this straight. Listen carefully. We're not going to call this straight, because what did we say straight means? 2 points and no angle. So what are we going to call this if we don't call it straight? We're going to call it linear. So guys, this is 180 degree angles and we call it linear. Notice that's not the same as straight. Straight is 1 bond, 2 points. Linear is 3 points and a 180 degree angle. So guys, let's look at the one example of this, which is carbon dioxide. There's others as well, but our example is going to be carbon dioxide, which looks like this. So guys, looking at the central carbon, do you see the 2 domains? Double bond, 2 domains. So guys, how many of those domains are bonding domains? 2. How many are non-bonding domains? None. And guys, carbon dioxide, this one's cool. Carbon dioxide looks like this. Double bonds. Not bad, right? So guys, what is the oxygen carbon oxygen angle? 180 degrees. What do we call the molecule? Linear. So this would be 180 degrees, and this would be linear. Now guys, notice again, hold on, wait, hold on. Notice again, guys, we didn't go 1 bonding and 1 non-bonding because that would just be undefined and straight. So guys, here's the question then. Don't put your notes away. You're going to need these. So guys, what is your homework going to look like? Well, let me show you. So guys, these are the directions for your homework. Don't grab your homework yet, just watch. It starts like this. Draw the Lewis dot structures. But then it says this. Identify the domain geometry and the molecular geometry and the angle. For example, PBr3. Guys, I copied this right out of your homework from a previous assignment. So let's look at PBr3. Here's what you've now got to be able to do. You've got to be able to identify domain geometry, molecular geometry, and the angle. So guys, watch. How do you do this? Well, go to the central atom and count the domains. How many domains are on the phosphorus? 4. So what is the domain geometry? Tetrahedral. Now we need to know the molecular geometry. So guys, check this out. We now know that there's 4 domains, right? So that puts us in the top table, 4 domains. But now, how many of those domains are bonding domains? 3. So that puts us then at this line with 3 bonding domains. So the angle is less than 109.5, and the molecular structure is trigonal pyramid. Does that make sense? So guys, 4 domains is a tetrahedral domain geometry. 3 of those are bonding domains, so that's a trigonal pyramid molecular geometry. The angle's less than 109.5. Let's do another one. Guys, what about O2? Which one is the central atom? Either one. So guys, say that you choose the atom that's on the left. How many domains? 3. So what is the domain geometry? Trigonal planar. Now guys, how many of those domains are bonding domains? 1. It's a double bond, but it's only 1. So guys, if one of those domains is a bonding domain, what is the molecular geometry? Straight. And what is the angle? Undefined. Anytime you've got one bonding domain, it's straight and undefined. So this would be trigonal planar, straight, and undefined. Now guys, the last one, HCN. How many domains on the central atom? 2. So what's the domain geometry? Linear. Both of those domains are bonding domains. So what's the molecular geometry? Linear, and the angle would be 180. So guys, let me just have an honest conversation with you. Every year, I have students on the test that believe that they are incapable of memorizing this, and they take the low road, and they make a cheat sheet, and they tuck it under their thigh, and they cheat on the test. Sometimes I catch them, and that gets ugly. Frankly, other times they write me letters before they go on their missions asking for me to forgive them. Guys, seriously, you guys understand that, right? Teachers at Orem High get those letters every year. You don't know that? Oh yeah, every year I get at least one, if not more, letters from students going, I'm sitting with my bishop trying to clear my conscience and I cheated my whole way through your class, please forgive me. Don't expect a reply if you write me that letter. So guys, you got to know this. You're going to find that as you get into this, you're going to find the patterns, and you're going to quickly find you don't have to memorize this. By the way, I'll also tell you this. This stuff about giving the names and the angles on the test will all be in matching. So guys, you don't have to memorize the names tetrahedral, trigonal pyramid, bent, straight, linear, trigonal plane. You don't have to memorize those. They're on the test. You just have to connect them up through matching. See what I'm saying? You don't have to memorize it. You just have to know what they are. So guys, with that said, grab your homework packet and let's get you done with your homework. You're still going to get it done. So where's the homework packet? Here we go. So guys, turn to the very back of your homework packet. Notice what the instructions say. Draw the Lewis dot molecular structures. Are you on number 5? Draw the Lewis dot molecular structures for the following molecules. Then identify the domain and molecular geometries and identify the angles. And right now, some of you are thinking, you have got to be kidding me. I've got to draw 20 more Lewis dot structures? Haven't we done enough of these? Now guys, turn back to assignment 4 and compare it to assignment 5. Do you see it? The molecules are the same. You have already drawn all of these Lewis dot structures for today's homework in the previous day's homework. I'm not going to have you draw 20 more Lewis dot structures. So here's what you're going to do. You're going to go back to your answers for the previous homework assignment, and you are simply going to write down the domain and molecular geometries and the angles for the Lewis dot structures you've already drawn. Do you see what I'm saying? So guys, how are you going to do this? You're just going to grab the double top secret decoder key. You're going to count domains. That will tell you the domain geometry. Then you're going to count bonding and non-bonding domains, and that will tell you the molecular geometry and the angle, with the understanding that you will not have these tables on the test. So guys, you now have 11 minutes. I think you'll get done. I'll put the answers on the wall. Kason has a question. No, just do it. Literally write these on the same piece of paper you did the previous homework on. So guys, let me stop recording and then I'll put the answers up on the wall.